Okay. Everybody, welcome. I really want to thank you for being here. I know it was at least I found it a very good evening last night. Perhaps a little bit too much drink, but also good company, so that's nice. But again, thanks for being here. It will be an interesting session, by the way. So it will be about optical communication networks and so on. There are three speakers: Josef, Klaus, and Rudolf will be talking, ranging from multi-vendor utilization of a fiber, passive optical networks, and then to at the end at the desktop. So more or less the whole spectrum we will go through. The first speaker will be Josef from Chestnut, long time active in the optical environment. Has even a few patents on his name. I got a prize for that, so that's great. So he's authoritative in this environment. And so I want to give Josef the floor for the coming time.
Okay, Victor, thank you. Thank you very much for kind introduction. So in my talk, I'd like to show some of our thoughts and experiences regarding the new applications which maybe need some extra bandwidth outside the normal transmission, and show our experiences with accommodating of these bandwidths. I'd like to also acknowledge my co-authors. This work has been partially supported by both two projects. And here comes outline. At first, just very briefly, I'd like to mention a few types of such demanding applications, and also discuss the possible ways how to allow communication of these applications. Then I'd like to show some practical experiences with transport of these signals in parallel with coherent transmission. Then again show some practical experiences with utilization of L band for transmission. And almost at the end, I'd like to mention and discuss possible utilization of S band or something really exotic like 2-micron bands. I think that it's quite obvious that there exists a lot of applications where statistical multiplex is not suitable or even usable. Typically, those are applications interacting with some external processes. Then the timing is crucial, and the delayed response decrease quality or simply the causes unacceptability of results. Such applications can be, for example, metrology, transmission of basic quantities like time, frequency, and frequency also means the length, because these days the meter is defined as a wavelength, not as a that rod. Also, these applications can be, for example, remote access control of instruments like a telescope or medical robots and so on. And obviously, systems of early warning or the gaining or collection of information from sensor networks. And based on presentations given in Tuesday, I think that also the really enormous data flows are not suitable candidates to use or to be multiplexed with other streams. With our well-known TCP, the multiplex of such streams typically cause significant decrease in performance of TCP, of enormous TCP flows. So in my next talk, I probably sometimes will use the name photonic service, and I mean here that photonic service is a dedicated connection or dedicated bandwidth between, obviously, typically two places in network, but it can also be some distribution mechanism, and it's described mainly by that bandwidth, photonic path, and we obviously want to be maximally transparent, so there is minimal processing on the side of network, and this path should be all optical. Definitely, it's not possible to fulfill every time, so we should allow as less of OEO as possible. So, yeah, I think that such defined photonic service can transport real-time data because the latency is stable and minimal, because it's only transport latency, and this service should also be stable because the bandwidth is allocated, and hopefully should be also transparent. So, okay, now we have a photonic service. We have applications, and now we have to connect the applications together. And here's one note that those signals can be quite untypical comparing with regular data signals. Typically, if we are transmitting 10 megahertz from optical clock, it's a 10 megahertz or maybe say 10 megabit signal. So it's very small, or even in case of transmission of a very stable frequency, it can be just carrier unmodulated. So the first choice definitely will be dedicated fiber. It's nice. You have your own fiber. You can do there everything. Yeah, but this option is suitable mainly for local loops, because in this study there are determined some average prices, and the prices are in this area for fiber rental. So means if you want to rent 200 kilometers of fiber, it will cost you a lot. So it's obvious that for long distances, this is economical nonsense to use dedicated fiber for every such connection. And we have to use dedicated lambda. Okay, into the same study, where are determined some annualized cost of typical, that study it's relatively old, so it was price of typical 10G transmission system, and the price is 1/4 of the fiber rental. Yeah. And typically in that times in that system was about 40 channels. Now it's we heard yesterday 80, 88, maybe 92 channels. So the annualized cost of one such channel is more favorable. Okay, great. So we create Li and wavelength in our system, but there will be a lot of parallel transmissions with our photonic service. Well, and maybe some of them will be coherent 100G. We heard it yesterday that amplitude modulated signals here designed as on-off keying have a negative impact on coherent now 100G transmission in near future higher, mainly through the nonlinear interactions. But we say this can be found almost in every paper or presentation regarding what to determine the precise number. It's really difficult. And what's really the shame that once you deploy such of lambda within your transmission system, vendors typically don't give you any warranty on performance of 100G coherent lambdas. Already mentioned yesterday, GAR bands will improve the situation. This number was also mentioned yesterday. You lose 2 or 4 channels, and situation will be better. So we decided to verify this influence in practice. First, in lab, we take two coherent systems from two different vendors and inject in parallel really slow signals, like 1 megabit or 100 megabits, because this signal was similar to the rate of our signal for transmission of accurate time. It serves for comparison of atomic clocks. And we take 1 megabit as a really worst case and put it 50 gigahertz apart from coherent 100G. Yeah, according to our observations, the prefect bit error rate was slightly different, but with more experiments, we dedicate this more to changes of gain in laboratory amplifiers because they weren't perfectly flat. So unfortunately, our observations are non-conclusive. Probably there are obviously some interactions, but in our experiment of 450 kilometers of fiber, both 652 or 655, these interactions wasn't definitely not principal and also wasn't observable. Again, mentioned yesterday, it will be different on 1,000 kilometer scales. Well, after lab tests, we have also done the field test. We run the photonic service for accurate time transmission here from Prague to Vienna. It's about 550 kilometers, and in this segment, which is about 300 kilometers, we run in parallel 100G lambda, and again, without no observable decrease or increase, if no observable increase in prefect bit error rate. So after, and I also should mention that this line is 655 with 652 local loops, which are compensated by traditional dispersion compensating fibers. So to say the conditions for operation of 100G are really, really poor. So after this successful verification, we switch into operation 100G transmission this February, and but with different vendor. But again, the effects are not effects of slow photonic service, slow amplitude modulation signal. Effects are not observable. So, yeah, this you can see very often that the available channels in our transmission systems are still decreasing and decreasing. For example, with 2.5G, it was possible to go really close. We had there 160 channels in only with 35 nanometers. How to say, maybe almost obsolete. No, I'm just kidding. 10G systems with 50 gigahertz spacing can offer numbers as I mentioned before, or in case of undersea system, it's possible to go up to 120 channels. Present system still fits into 50 gigahertz grid, offering these numbers of channels, but again mentioned yesterday, there's probably no chance to use this grid for future transmission. So it means that in future system there won't be 80 or 90 parallel channels. There will be maybe 40 parallel channels. So the number of available channels is decreasing. Obviously, it's possible to start to save a spectrum, use more advanced signal modulations, reduce the grid, or maybe there are possibilities to use a flexible grid with adaptive transceivers. This means with short distances, good roads, you will use very efficient modulation, say spectra. For bad links, long distances, you will use broader modulations. But There are some presentations and articles stating that savings of spectra can be up to 30%. It's nice, 1/3 almost. But everything leads to the higher channel density and higher spectral utilization, and this can be maybe in contradiction with demand for the spectral separation of photonic services. And here I'd like to skip to part of presentation regarding L-band, S-band. Everyone knows these pictures. Here is conventional C-band, but also single-mode fiber shows reasonable low attenuation in L-band, which is sometimes used but not often, and also the S-band. Well, what's nice that in L-band we can also use our well-known matured erbium dope amplifiers. So we decided to verify this possibility and to gain some practical experiences. So again, we start in lab, prepare a setup of one quite long single span of 150 or 200 kilometers, and try to overcome it at once. Obviously, it was possible, but what I'd like to show here, even here, these are signals in C-band, signals in L-band, and the spectral distance is about 60 nanometers. And even here, it's possible to observe Raman effect, that this channel is pumps mainly this channel and causes the depletion or decrease of power when I switch the signal. The signal drop about 0.6 dB, so it can be tricky in case of long distance transmissions. And why we choose such strange scenario of one long hop? Yeah, because in next step we deploy this parallel transmission on experimental facility where we have one really weird segment of 40 decibels. So this picture shows the final field deployment on 300 kilometers long line. Yeah, and what's not shown here, the system also is chromatic dispersion compensated and works with any problems. So I also indicated that there is available S-band, almost 90 nanometers of not 90, 80, 85 nanometers of spectrum. It's nice, but unfortunately it's necessary to change the rare earth from erbium to thulium. But the pumping scheme is quite different. With erbium ions, it's quite simple, up conversion with pump, and the stimulated emission, the drop. In case of thulium, there are two up conversions and two spontaneous decoys. And unfortunately, these decoys are quite high in silica fibers, so typically for this single pump scheme are fluoride fibers used. Such amplifiers are commercially available, showing relatively good gain, but the problem with fluoride fibers that they can't be spliced with normal silica fibers, and they are quite hygroscopic. It also has been proposed some schematics to achieve gain in S-band with silica fibers using two different pumping wavelengths, but unfortunately these amplifiers are not commercially available. So we also have considered the third option to use matured ETFA for this small region, because they also can have the reasonable gain, but they are commercially available. But the noise figure can be high like 8, 9, or even 10 dB. But unfortunately, we stopped these experiments mainly due to commercial unavailability of transceivers for dense multiplex for this region. It's a pity because the remaining components are on the market, like maxis, demaxis, dispersion compensators, and so on. And this is just a curiosity. The thulium also, you probably remember this picture, the thulium also show nice transition here, but this falls into the 2-micron band. The team of Dr. Lee shown experimental operation in these 2-micron bands with really broad bandwidth, more than 100 nanometers, with really high gain comparable to EDFAs, and realized in, say, the proven technology and reliable technology of silica glass. Yeah, but 2-micron band, it sounds strange. Yeah, it's really strange in conventional fibers. The attenuation is in order of hundreds decibel per kilometer. But there have been also significantly progress on hollow core. You see the hole instead of solid core. In hollow core photonic bandgap fibers. And what's nice on these fibers that here is air or other gas, so the effective refraction index is close to 1, so the propagation speed is not 2/3 of c like in conventional fiber, but it's almost c. So maybe this can be, how to say, the important issue for next works into these fibers, because already mentioned the banking or trade applications really need the minimal latency. What's also nice, the nonlinearity here is really low. Obviously, the best manufactured fiber today shows, let's say, 20 times higher loss than SMF, but there are theoretical works that these losses can go to really nice number. And I'd like only to mention that the first fiber of Charles Kao, who holds Nobel Prize for its work, the attenuation of the first fiber was into this number, 1000 decibels per 1 kilometer. So maybe also the attenuation will be improved here. So I'd like to conclude with no conclusions, but observations. Yeah, definitely we need to more verify the parallel operation of such strange signals. Yeah, the building blocks for transmission system for L-band are commercially available, but what was really curious that we wait almost 1.5 years for transceivers. Well, obviously there are some issues like power transients between the systems and also the macro bending losses. If you bend your cable in C-band, nothing happens, but if you do it at the end of L-band, yeah, attenuation increases significantly. Okay, but we still, but we postponed our plans with S-band, as I mentioned, because of unavailable transceivers. I'd like to here acknowledge my colleagues, and especially Miroslav, who passed away this April. So thank you very much for your kind attention, and please do you have questions?
Yeah, thank you very much. So questions? Okay, while you're thinking about it, and please think about it. I know it's difficult to get started in the morning, but I have a question. It is about, let's say I'm going to do a call for tender for optical equipment, and I want to make sure that my optical equipment, let's say our present day optical equipment, can handle foreign wavelengths in the 100 gigabit area, or 100 gigabit, yeah. What should I specify so that the vendor knows what I'm asking for? So it's about a multi-vendor environment, and how can I squeeze the best out of these vendors? Because now you say, oh, we don't guarantee anything anymore. How can I overcome that?
Yeah, it's really good questions, and sometimes I also asking myself how to do it. Yeah.
Do we need to help them with answering that question, or would they know it themselves? I could ask that question later to Klaus also.
No, basically, I think that typically vendors are nice, and okay, you receive unofficial approval, for example, for operation of aligned coherent channels, because it was also mentioned here yesterday, they are also phased coded, so the interactions will be less harmful than in case of on-off keying. And yeah, and also they will be in power equalized with your, how to say, native channels. So yeah, in my opinion, there shouldn't be problems, but to receive a guarantee for such operation is difficult, and very frankly, I don't know how to push the vendors to guarantee you that your system will operate with. But it has been a lot of, how to say, demos done by Surfnet, done by Nordunet. It works without any problems.
Yeah. Okay. Thanks. Okay. Questions. I come back to you. Okay. Thanks very much again. So the next speaker is Klaus from Adva Optical Networking. So he's a vendor. So perhaps he can already think about.
Oops, sorry.
Klaus have been quite busy also in the optical environment. I think for some 20 years around that. WDM, PON environment and the standardization, and also you have a few patents, I think, under your name. I understand. So. We are in authoritative presenters over here. But this time, Klaus will talk about all the different PON technologies which could be utilized in the metro and the campus environment, let's say in our NRN environment. So it will be quite interesting to see how we can utilize this as a provider, or as a campus provider, or as an NRN. So the floor is yours, Klaus.
Thanks, Victor. Morning, everybody. Yesterday I talked about long haul and high speed, layer 0, and today I'm going to talk about. I first have to find out how to help this. About the other end of the WDM scale, about access or maybe backhaul and low cost WDM. I'm not talking about any possible PON systems that would require an overview on APON, BPON, GPON, EPON, XGPON, and NGPON2, which I could give next year because I'm now working for more than 3 years in FSAN standardization. If that would be interesting, I'm happy to give an overview from there. But today I restricted to what might be called WDM PON, or what started with what is called passive WDM, and there is a transition between the two, and which most recently indeed has make it into at least as part of the NGPON2 standard, the upcoming NGPON2 standard, which is currently being worked on in FSAN. So there is only 2 topics I want to talk about. It's first chapter is on passive WDM, because I'm not 100% sure that all of you know the concept, and then a couple of slides on WDM PON. And as I said, it's about low-cost access, which might or can go down to the end users. From today's perspective, unlikely that we will see WDM PON within the next, say, 10 years going to residential end users. In the residential area, it's likely to be the GPON and its successors. So what is passive WDM? That's relatively simple to explain. If I have a certain, is this the laser pointer? Yes. Application here, we show a switch, for example. We can either connect it for transport purposes to a WDM transport system, or we can go for the passive WDM approach, which also was known under the term of Blacklink. That is, I plug colored interfaces into the end device and connect these to, well, a passive filter. That's where the name comes from. So basically I do avoid. Well, yes, that is a good question. What do I avoid? I don't avoid transponders in a certain sense, because of course for transport I need the, let's say, high performance colored interfaces. That is exactly the ones I do not avoid. I do avoid OEO in the sense that I don't have the duplicated gray interfaces. I also lose lots of functionality, because if I do exactly this here, I more or less don't have any view on what's going on. I lose lots of OAM functionality. So in effect, there are pros and cons. Certainly, so this, for example, may be a little bit lower in latency, because if I avoid whatever transport card, particularly if that one has framing and possibly also multiplexing on board, then indeed I would avoid some latency. I certainly should end up with lower power consumption, which might be interesting in certain cases. Maybe I also have a little bit better MTBF, because the whole system is less complex, so there is less risk to fail. But I usually don't have performance monitoring, etc. Also, amplification is a little bit tricky, because, well, I don't have a proper transport system in that sense anymore. And it's more or less vice versa here. I do have all the performance monitoring capabilities, etc. I will see higher power consumption. That's because I have better functionality. And yes, to a certain extent, of course, this will cost more. But keep in mind, I don't avoid the colored interfaces, the costly ones. I get rid of the cheap gray ones, and I get functionality. So if I really win on operational aspects, that is typically accepted with at least certain network operators to pay for that functionality. Okay, there was the overview. So this is what can be called passive WDM. Here it's shown again. So I have my clients here. I can plug the colored interfaces, which at 10 gig would be XFPs, and at 1 gig or 2.5 gig could theoretically be SFPs, but I'm not aware of such massive applications. So it's mostly today really XFPs and 10 gig. There are some aspects. In this case, obviously, if I used a fully blown DWDM system, I need the respective number of spare parts. That is, I need a certain pool of, for example, of the colored XFPs, which is okay, but I come back to the spare parts thing. And for setup, I obviously need to correlate the near end pluggable and its port here with the far end pluggable and that port. And there is nothing that tells me I'm doing everything right until the end-to-end connection is working. So that's also a difference as compared to transport systems. And as I already mentioned, normally I would not have these monitoring capabilities and a visualization of in-service wavelengths unless I use an external device like an optical spectrum analyzer. So yes, it is relatively simple. It looks relatively simple, but as said, I'm lacking certain functionality, and I have at least to be a little bit careful during setup. Now that brought us to an idea. How would it look like if we combined the best of both worlds? So let's try to get as close to this one, a passive WDM system, but let's also try to get as many functionalities out of this here as possible. And this brings us to a concept that might be called smart passive WDM or whatever the term. It is possible to combine the two worlds to a certain extent, which is quite a good extent, by the way. For example, to now use directly plugged into the end systems the tunable XFPs. Now, a normal host, like a switch or a router or a director or whatever that is, would not be able to perform the task of tuning. The device isn't built for it, so it doesn't know what tuning is. So we need something in addition, something we call a tracer, which sits in this case on the other side of the filter, but which allows to use tunable XFPs in this case, and later the upcoming tuning SFP pluses. This also allows up to 96 wavelength space, 50 gigahertz. So there is a slight increase of resulting capacity. And setup gets a little bit simpler because the only thing I have to do is I have to correlate this port with the respective other one. But I can plug, since it is a tunable pluggable, I can plug that or connect it anywhere here. And I will come to the tracer. The tracer will perform the task of tuning and give us a certain degree of monitoring, etc. So what I, amongst others, gain is I can use a universal pluggable now, which simplifies spare parts, obviously, which simplifies to a certain extent the setup, and via the tracer I get some supervision capability. One slide on the XFP. For the client, it is a standard XFP. Of course, anything else wouldn't be accepted. It of course requires some addition because I need to be able to communicate with the XFP from the outside, from the tracer. So the XFP gets a minor addition, which in the end enables us to establish a communications channel. And the communications channel, of course, has to be fully transparent for the payload. So it's typically it can be implemented as an RF overmodulation. And yes, there is a certain frequency band between the erbium lifetime, if there were any erbium amplifiers, and the lower edge of any transport protocol. So there's the range around what is it, a couple of megahertz can indeed be used for RF pilot tones. So that's how one can establish the communications channel, and then I can, as mentioned, use tunable pluggables, which is pretty elegant on the one hand side, and in some other applications it's simply required. So there are some applications where the respective network operators simply say, I do want to have what is also called colorless transceivers. Colorless meaning I do not allow dedicated wavelengths, fixed wavelengths transceivers. So that would be one problem solved. And the tracer, by the way, this is very simplified, but would look like this. It has receive capabilities and also transmit capabilities for the RF pilot tones, for the communications channel that I need to communicate with the pluggables. And hence, the tracer can tell them, because it sits seen from the transceiver, it sits behind the filter. So I pass the filter already, and the tracer consequently can tell the pluggable where to tune to. And it can also monitor it to a good extent. So this is how a relatively simple tracer unit. These are low-speed components. So in effect, it's a relatively cheap device. It doesn't add massively to cost. So that's how one can establish what might be called smart passive WDM with reduced spare part, with simpler setup, etc. And which also can give us some monitoring capability. So if I connect the tracer to whatever management system, I can see which channels are active, etc. And yeah, this is a simplified flowchart as how the pluggable goes online. Which brings me, there's one next step of this. So today this would be based on XFPs, as I mentioned, simply because they were the first pluggables which are tunable. And I have no precise idea how long it will take till the tunable SFP Plus really becomes generally available. It of course exists already in prototypes and we can test it, etc. But it may take another year or so. So then the concept can be copied to the tunable SFP Plus, which also means the concept wouldn't cover 10 gig exclusively, but anything between 1 gig and 10 gig in terms of the bit rates. And an example outside the NRAN scenery, but where we see a good fit for this would be mobile front haul. Front haul is the transmission between the mobile base stations and the remote radio heads, just to mention it. But it would also make a good fit in backhaul or broadband access or business access. So maybe it is something that might be interesting for connecting whatever dispersed sites on a large campus, for example. Okay, this brings me to the WDM PON, because that is technically not far away, which you can see here. Again, well, pluggables maybe, again a tracer, and the only or main difference now is it's not necessarily point to point, but it can be point to multi-point physically. So and this structure would then obviously be called a PON, and since it is based on WDM, we can call it a WDM PON, and this would be one solution as a pretty early but pretty capable WDM PON can be built. I mean, there is, I don't know, 2, 3 maybe commercial WDM PON products out there which are not based on tunable lasers, but on a completely different technology, which the one way or the other is less capable than tunable lasers. So you would have massive difficulties, if it's possible at all, with 10 gig services. You would have difficulties with distances above 20 kilometers and so on and so forth. So those who are deeply involved in WDM PON technology believe that the end game of these PONs will be based on tunable lasers. So as said, with only very minor modifications, possibly this tracer would also have to serve these pluggables here, which can be made the one way or the other. Either the tracer directly talks to these, or the tracer talks to the local transceivers, and the local ones talk to the remote ones. So there is several ways to establish the necessary communications channels. Yeah, if this here, oops, sorry, wrong button as usual. If this here was a large campus area, then possibly such a WDM PON may be a good means for connecting the users here with broadband services, 10 gig or so. And it could later be upgraded to other bit rates, of course, either smaller ones or maybe possibly 28 gig or something in that arena. This is more or less the same picture, but the evolution. It shows the evolution. This is what we also now discussed since 3 years in FSAN standardization. So the guys in FSAN really are after a low-cost tunable laser. Low-cost meaning something I almost don't want to mention it, but they are really talking about a sub-$100 unit. I'm not 100% sure if a high-performance tunable laser will be broadband tunable. They are talking full C-band or L-band. If that will make the sub-$100 arena, but it's certainly cheaper than a tunable XFP. Then it needs possibly a little bit of modification, because in order to make a laser such cheap, I may have to avoid certain subcomponents like the dedicated wavelength locker, or maybe even the cooler, etc. So if that piece here doesn't have its own dedicated wavelength locker, I also need to do the complete wavelength locking via the centralized head end, which, by the way, in typical PON terminology is called the OLT, optical line termination. So I may have it may not only the setting of the precise wavelength channel, but also the fine tuning within that channel may be a task that runs via the OLT. So here's the closed loop control indicated as a dashed red line. So that would be the evolutionary path. Today we don't have such lowest cost lasers. There's heavy discussion when they will become available. I think within the next 3 years, maybe, possibly, depending on what exactly is going on in PON standardization and whether or not such a device, a broadband tunable, really will be required. This here basically is part of the latest NG-PON2 discussion. So hopefully these lasers become available, and then a modified tracer unit, which also performs the task of fine tuning, may be used to build a nice, powerful WDM PON. So this is how it may look like in 3 years from now, and I'll let you know when it becomes available. One thing, PONs normally use or make use of single fibers only. This is certainly not a drawback, because if there is fiber scarcity, it's always good to just use one instead of two. How then is upstream downstream performed? Typical setup would be using C-band for up to, where is it, 96 channels possibly, or 84 channels if it's 100 gigahertz in the upstream direction, and using L-band in the downstream. It's two non-overlapping bands, and they are traveling in counter directions, so there is no interference between the two. But how do I do it in this device, which is typically accommodated in a passive remote node? RN stands for remote node. It's an AWG, yes, true, but it's a special AWG. It's a cyclic AWG. Now, typically all AWGs are cyclic. All filters, by the way, are cyclic. They can be used in multiple frequency ranges, but these specially designed cyclic AWGs support on the fan-out ports here one channel in C-band plus one channel in L-band. And by the way, they also support one channel in extended L-band and upper S-band and lower S-band going down to the O-band, etc. We have tried to measure it, and with very little increase of the insertion loss, by the way. We have tried to measure it in the lab, and our limitation was the frequency range of our measurement equipment. So wherever the fiber is low loss, you can use the cyclic orders of a cyclic AWG. I'm mentioning it because cyclic AWGs have some other nice capabilities. The only thing possibly to mention is if a cyclic AWG is, for example, 100 gigahertz in C-band, it can't be, for physical reasons, exactly 100 gigahertz in the other bands. It will deviate. And the further I'm away from, in this case, the C-band, the more it deviates. So you end up with having to deal with off-grid wavelengths, which is, by the way, no problem as soon as I use tunable transmitters, and then I tune them to the off-grid wavelengths, no problem. Why I am mentioning cyclic AWGs are, by the way, they have been standardized in ITU recommendation G698.3 with today 48 ports spaced nominally 100 gigahertz. And as I said, I can use all the other cyclic orders as well. For example, in PONs, we typically use the U-band for monitoring. I can do it. I can do monitoring systems for the monitoring of the power of the fiber plant in the U-band. I could extend it into S-band, just as Josef indicated. I can... And yes, these devices, by the way, can also be made athermal, so they can go in outside plant. And since AWGs, in effect, if they were N by M devices, translate rows of wavelengths into columns of wavelengths, they could have at least two nice additional capabilities. The one I already mentioned, I simply reuse other orders, cyclic orders of the AWG, for example in U-band for monitoring. I could then place a passive partial reflector, for example, in front of the client devices, and I can sort of passively ping this reflector, and so I see the fiber plant is intact up to the client demarcation point. Very nice. But I could also use cyclic or 2 by N AWGs in this way. I could use or provide a second feeder fiber here, which without additional insertion loss here gives me protection for the feeder fiber section. The feeder fiber section is obviously that section which carries the multiplex section, that is all the signals. So if that guy here fails, all the signals here are down. If one of these fibers fails, it only affects a single customer. So there might be some interest to protect the common section, which is normally called feeder fiber section. This can be done with or cyclic AWGs as well. Which is also maybe a development step for future WDM PONs. So that brings me to the end of my overview on passive WDM and WDM PON, and I'm open to questions.
Thank you very much.
Okay, thanks. Interesting talk. Different than the other one, but it's good to hear all the ins and outs around PONs. Questions? I think there's a microphone coming for you, so the world can hear you.
Okay, Klaus, it was really nice presentation. I have two questions. First will be, please could you comment the bending losses in U-band? Is it possible to use that OTDR on standard 652.D fibers?
Yes, I mean, true, and you mentioned it already, banding loss or macro banding loss is increasing in the 16 or towards higher wavelengths, true, but the U-band typically is used in PON. It's reserved the area above 1625, so 1625 to 1675 is reserved in standardized PON for OTDR monitoring. So my guess is everybody assumes that once the fiber is cabled and laid, it's there. And if there's a sharp band whatsoever, well, it is monitored once, and then you know there is a band. So it's yes, the insertion loss is increasing, but I can still use the U-band for monitoring.
Okay, thank you. And second question was that cheap lasers, they aren't based on reflective SOA technology, aren't they?
No.
Yeah,
the reflective SOA would be
okay.
the alternative technology which is used for commercial WDM PON today. But they are exactly the devices that I mentioned. They have a massively lower product of bitrate and reach. The low-cost laser would be a real low-cost laser, and it wouldn't even be a DFB laser. It would be a derivative of a DBR, most likely. Okay. Maybe a tunable VCSEL, I can't tell. But the tunable VCSEL would have the disadvantage of relatively low launch power. We are honestly, we are after low-cost DBR.
Okay, thank you.
Yeah. Other questions? Okay, then I want to thank Klaus again for this. Okay, then we come to the third presenter, Rudolf from the University of Twente. He has done there his bachelor about how to offload IP networks using, let's say, light paths. Yeah. So it's a little bit different. We will hear now, as part of his master's, that he's looking at the how do I extend light paths, which are Ethernet links, perhaps. I'm sorry, I'm translating, but you can rectify me how you can extend them in a dynamic way to the desktop. Normally, these things only exist in the backbone. I think you are looking at how to do that, through campuses towards the people at home. So that will be an interesting talk, and I give you the floor for that. Thanks very much.
Yeah, thank you for your introduction. Let me see. This is the last slide. Why is it? Yes. Okay. As Victor already told, this talk is going to be about extending dynamic light paths to the desktop. It's work that I've done. It's a collaboration between SurfNet and the University of Twente. As mentioned already, it's part of my master's thesis. I am going to talk first a little bit about an introduction. Then I'm going to mention the goal. So I'm going to explain a little bit about the approach that I have used for this, and the results, and finally conclusion and some future work. First, as you already know, there are many applications nowadays that use the internet for communication, and they do that on the best effort way, and that's fine for many applications. But some applications really do need to have more quality of service. As you all could see in the demo area, we have one of these haptic devices, and such applications really need better connections than the internet often can offer. So that's where light paths comes into. By applying light paths, it's way better to provide these kinds of quality of service. But however, if you connect a light pad, it's very often a static way of connecting devices. And for example, like the demo that we have here, it's a connection that is established for only this conference, and after that, the whole connection will be torn down. That could be a very expensive way of connecting devices and connecting applications. So this is where dynamic light pads may be a solution. On the moment that a dynamic light pad is not used anymore for a certain application, you can free the resources for another application. So dynamic light pads are already available at the NRANs. It's even possible to establish dynamic light pads over multiple NRANs. Also at this conference, demos are shown how this works, and it works pretty fine. But now it's very wonderful that NRANs are able to do this. But really, the trick is to extend a dynamic light pad also to the device or the workplace of the user, and that's where this work is focused on. Currently, now it is the case that when a researcher wants to have a light pad, someone needs to go any campus network to connect physically a light pad before someone can use it. Well, obviously this does not really scale. So the situation that we would end up to is desirable, is some scalable, generic way that we can, in a flexible way, can connect the researcher with the dynamic light pads that are offered by the NRANs. So, in order to make this available on a dynamic, in a dynamic way, we first have to look at what is available. It is not reasonable to think that on a short notice, campus networks and are able to invest into a dedicated level 2 network besides their existing packet switch network. So in this study, we looked into how it could be made possible to transmit the data that is from the dynamic light pads over the existing packet switch network, while keeping the same properties, the same characteristics as a light pad does. So in this context of the work, a light pad is not necessarily an optical light pad. Indeed, as Victor already told, it is in fact a connection over a packet switch network while keeping the same characteristics. So first thing to do is to determine what a dedicated light pad, what kind of characteristics it has, what kind of properties it has. After that, it is useful to look at the alternative, making a light pad over a packet switch network, determine the properties and compare them. So the focus of this study was the last mile, as in the University of Twente campus network. By this we are looking at a situation where we are restricted by existing hardware that is available at this moment for the campus network. So we decided to to look at VLAN solutions and MPLS solution to extend these dynamic light paths. So the goal is to investigate the transmission characteristics of a light path and what happens if you put a light path, you extend such a light path to the existing routed traffic or background traffic. So what is really the interference of those two if you do such a thing? So what did we do? We measured the performance of a light path by 4 different aspects. We took a look at the throughput, the latency, the jitter, and the amount of packet loss. And those are the 4 things that we use for determining the characteristic of a light path. We determined 4 different scenarios for the last mile to transmit these light paths. First, as a reference, we looked at the dedicated, physically isolated light paths and determined the characteristics of it. In that case, we looked at the situation. What would happen if you transmit a light path over the campus infrastructure while using a best effort method? And the last, of course, in the VLAN and MPLS situation, we tried to establish a path to the campus network and offering a very high quality of service, and looked at the results. So for the quality of service, in case of the VLAN, we use the priority code point bits. So we have we can determine 8 different classes, and also in the case of MPLS, we use the experimental field is used also 3 bits. So they're in quality of service wise, you can compare them. They're more or less the same. We also apply policing to really being able to tell the network how much bandwidth is available for a light path. And for that, we configured 2 different parts in the network: the committed information rate, more or less the amount of bandwidth available for the light path, and committed burst size. Also, the priority scheduling, we used a strict priority method, and we configured the light path having the highest priority. So that's, in that case, the light path traffic will always be served first over the best effort network traffic. These are the different scenarios used for the testing. The first one is the dedicated light path, here shown. This one is more or less the same idea, also a light path, a dedicated light path, only in this case the switches are in between. So yeah, it is also a dedicated light path without any other cross traffic. And the last scenario, this one, is used in the two last scenarios, where we have a light path traversing over the packet switch network, and here the background traffic. Okay. So let's have a look at the results. The dedicated light path, being this upper scenario, The dedicated light path we see with TCP traffic the throughput being almost the same as we have determined in this scenario where the traffic is passing the switches. With the UDP test, we have we see here the speed, the throughput of the test. So we configured the UDP stream to transmit at a certain rate, and we can see here that the difference between the dedicated light path, as in the isolated, physically isolated light path, and the switched version are really close to each other. So the except for this last one, they're really performing alike. Also with the jitter, we see a similar thing happening, where the light path, the dedicated light path, and the switched light path are really close to each other, performing almost alike. Here with the losses, we see a little bit of losses happening with the increase of the bandwidth. I have to mention that we did these tests with iPerf. So in fact, what we are measuring is between two applications, and the losses that occur here in this figure, we could also see them in the kernel. So it actually, what we actually see here is most of the packet loss occurring on the machines itself, and not really by the switches. Here we see the amount of data transferred according to the configured speed. We see nicely that also both the dedicated light path as well as the packet switch light path have the same performance and do not really differ that much. Here we see a scenario where actually the third figure is used, this one. Here we see a typical behavior of two TCP flows competing for bandwidth. If we take a look at the total test run, it's a 10 minutes run where the beginning phase, the background traffic exists already. And here at 90 seconds, the green line is the light path that is starting to send as well. And if we take a look at the total throughput, between the 90 seconds and the 480 that the light path is transmitting, in that time interval, the background traffic and the light path traffic are almost sending the same amount of traffic. So they're really dividing the available resources. Also with UDP, this can be shown really nicely that well, the difference between those two are even closer. Another scenario that we looked at is the TCP-UDP combination, and that's really an interesting situation where we can see that where the background traffic is existing here at a very high load, and as soon as the light path traffic starts, we can see that the existing UDP traffic of the background is totally pushed away, and this would be a really undesirable situation for a campus network. So, and this is where the high priority packet switch light pad may provide a solution. Actually, they do. In this case, we configured the light pad with a committed information rate of 500 megabits. And in this case, we really see that the light pad is not able to gain more bandwidth than is configured. And in this case, we also see that the bandwidth is the resources are divided nicely. And even if the bandwidth, the light pad is trying to gain more, the amount of resources are divided nicely. The only thing is that if the light pad is transmitting more than the committed information rate is configured, then we see a slightly increase of RTT and jitter. In this case, I want to show you the difference between the best effort method, where the light pad is experiencing a certain jitter, and in case of the high priority light pads, we can see that the amount of jitter is really improving, although the background traffic is experiencing a worse jitter. We also did it with the RTT, with the latency. And also here, in this case, you can see a very good improvement over a slightly less latency for the background, as the graph also shows. The previous example of is a VLAN high priority packet switch light pad. We also looked into the MPLS version of it. So what I did here is every dot is an average of 10 tests of 10 minutes. And we took an average of that. And this nicely shows that as well as the MPLS light pad and the VLAN light pad are gaining a certain amount of resources determined by the SER value, the committed information rate, and the other available resources all go to the background traffic. So also in this case, MPLS and VLAN are performing alike. Now in this case, we see sort of a worst case scenario where the background traffic as well as the light pad are trying to send more data than is available for resources, on the resources. So it's sort of a worst case scenario. In this case, we see that when the light pad is given a committed information rate of 100 megabits, and it is sending with 1,000, we can see that the latency is slightly worse than the background traffic would have. In this case, the background traffic should be able to have 900 megabits available resources. And very quickly, we see that the performance of the light pad is improving due to the strict priority scheduling, and that indeed the background traffic is the latency is getting higher by when the light pads are gaining more resources in the network. With jitter, we saw a very interesting situation where this line is showing the jitter of the MPLS light pad, and the jitter is way worse than the background traffic or the VLAN situation, VLAN priority switched LiPad. Let me see this. This pink one or magenta, cyan color line is the VLAN LiPad, and is performing in this situation much better than the MPLS situation. The exact reason for this is I haven't been able to determine it exactly, but what I have seen is that this is very bursty jitter, where this situation is of course not very likely to happen, or at least it is more likely that a network operator will check for the available bandwidth, or the resource management system will check for the available bandwidth, and therefore a situation where the LiPad is sending more or less what is available on resources more likely. So we also did a test where the background traffic is 950 megabits minus the CF value, and the LiPad is 50 megabits below the CF value. And in this case, we see that there is almost no difference between the MPLS and the VLAN situation. And also for the jitter, we did the same observation, that the LiPads are performing alike. And in case of the MPLS, the red one, the background traffic is even improved compared to the VLAN situation. So in conclusion, in a situation where we look at the no congestion, so no cross traffic, well, we can say that the packet switched LiPads could be used as an alternative for really dedicated LiPads, where a network operator needs to connect a LiPad physically. And in the congested version, we could say that when we use a packet switch LiPad in combination with quality of service and with policing, we are able to provide an alternative for the physically isolated LiPads. So towards for discussion and future work, this work that I have shown you now is performed with iPerf. What we are looking into is to do these tests also with more representative background traffic, where we could, for example, use more realistic data out of the network that we observe, and try to see how that would influence when using the dynamic or the packet switch LiPads. Also, doing tests over end-to-end remote locations might be interesting to look into, to see if there are any unforeseen challenges with multi-vendor situations, for example. Another thing is the whole resource reservation and provisioning might be useful to look into the RSVP to make that a more automatic process. Also, the question how to implement packet switch networks in a campus network might be an interesting question. Do we want to provide dynamic LiPads or LiPads, packet switch LiPads all the way up to the end nodes, or do we want to have them in a cloud or to certain rooms within a campus network? Might be an interesting question. And last, of course, the holy grail to develop a network resource management that is able to establish these packet switch light pads on a dynamic and automatic way. So that's what my talk was. Any questions?
Thank you very much. So it was different than the optical view, I think, and this is about a little bit higher up and up to the desktop. So are there questions for Rudolf about this? Over there, thanks.
I suppose your light pads were dynamic in a way.
Sorry?
Dynamic in light pads. The way you were setting up light pads.
No, in this case they were manually configured.
Oh, okay.
Yeah.
Because I was sort of going to ask how far are you from the actual API setting up light paths rather than doing by yourself. But then. Okay.
No, that's really the next step up. This was really a research to determine what techniques we want to use, and now the next step is to actually work on an API or an automatic process. So that's really the next step. Yeah.
Thank you.
Related perhaps to that, dynamic networks are nice perhaps in the core, if the NRN even wants to do that. But the local, let's say, campus could have more problems in making things dynamic. So, and that are normally not technical problems, but that are human or social or problems that people just don't want to have people meddling with their own network. Is that part of your study of how HANet clients will react on that control that they want, or that their own researchers want, by the way?
Well, that might be maybe even more political issue, and that's not part of my research at the moment. But the wish is really to have a dynamic automatic system. So I'm not sure on what time scale that comes available. But I think the wish to have such a system is really there.
Okay.
So, yeah.
It would be nice because the University of Twente has a very strong human department or human, teaching, sociology and that kind of thing. So perhaps you could see if you can combine that knowledge with how to convince clients to be more open to these kind of dynamic things. So.
Yeah, it's really probably more about thinking about use cases and exactly. Yeah.
Other questions? If not, then no, I have one question more. Then let's say you had VLAN and MPLS, and perhaps I didn't look at all your slides properly enough. Mm-hmm. Is the VLAN using a real Ethernet switches, and the MPLS is on an IP routers, or are they both using MPLS?
The VLANs are configured really as Ethernet on top of Ethernet.
On the Ethernet switches.
On the Ethernet switches,
okay.
Yeah. And these switches are also MPLS capable, so they're exactly the same switches.
Same switch. Okay.
Yeah.
Okay. Thank you very much. Another question that popped up from people. Okay. Now I want to thank all the speakers for their interesting ideas. Thanks. And before you leave, I have some general points.